Yes, we are continuing with the integration of exponential functions. There is something which I wanted you to know about this morning as we continue to integrate these functions. We have what we, because in some occasions, one may not easily know what to rate to be u or dv dx, especially when we start functions that have exponential and trigonometric functions which have logarithmic functions with the polynomials and inverse trigonometric functions. So one may not easily know what to rate u or dv dx. So there is this term called LIATE. We normally use this thing, LIATE, whereby L stands for logarithmic functions. So in all the expressions where you have a logarithmic function, you should always rate it to be u. In other words, you choose u to be the function that comes first in this list. This is the list you have, but if we have like maybe one may have something like ex, maybe it's an x. So what comes first in this, according to what you're given, is what you rate. For example, here we have exponential function and trigonometric function. You have exponential function and trigonometric function. Now, the trigonometric exponential function comes last. So you rate the trigonometric function to be u and the exponential function to be dv dx. So this one is exponential function. This is the inverse trigonometric function, inverse trig. This is the algebraic function, algebraic like x squared x, something like that. Then this is a trigonometric function, and then finally exponential. So in all cases, the exponential function can always be let to be dv, can always be let to be dv dx. Now, based on what we have been covering, we can continue by having example, but this thing, this LIATE or LIATE, whatever form you may call it, it can work for you better, whereby you choose u to be the function that comes first in this list. You may have maybe xe to the power x. Because x comes first, rather algebraic function comes before exponential, we rate this one to be u and this one to be dv dx, something like that. So you may not spend too much time looking for what to rate to be u or what not. Okay, now here comes some other cases that we did not integrate last time, and I want us to integrate a function. We are continuing with the integrals of polynomials and exponential functions, directly from where we stopped last time. So we are going to have an integral of x 2 power x dx. One may look at this thing as very small or too simple, but it may take you very far. This one may take you very far depending on the attention that you give it. Now, of course, we have x and then 2 to the power x. Now, the logic that we employ here is to just let u, our u will be what? Our u will be x, and our dv dx will be 2 to the power x. So, of course, we have to differentiate. So du dx is what? Is 1. after differentiating u, you'll get 1. And then v, of course, v is gotten as a result of integrating 2 power x. When you integrate 2 power x, who can tell me what we get? If you integrate 2 power x, this is something that can take you very far. We may think that it is something very simpler, but it can take you quite far. So when you integrate 2 power x, you get that 2 power x exactly. Then out of ln 2, I'm going to prove it here so that you don't get confused. We are going to check out for an integral of 2 power x dx. What we need to do here is to let, we shall let u to be the whole thing. So u will be equaling to 2 to the power x. Then introduce ln both sides. So it will be ln u. If you introduce ln both sides, it's going to be ln u is going to be equal to ln 2 to the power x. However, there are some people who overread. The moment you overread, or the moment you read different sources, you're going to find them using a different approach, but this is a bit easier. Introduce ln both sides. Then after introducing ln, continue and say that ln u is equal to drop x, so it is going to be x ln 2, x ln 2. Then what you do, make x the subject. Okay, so our x is going to be equal to, equal to ln u out of ln 2. So after getting this, differentiate both sides. When you differentiate both sides, here you will get dx is equal to 1 over ln 2. Ln 2 is like a constant. So I can say 1 over ln 2. Then when you differentiate ln u, you get 1 over u. Then du. So because it's like when you have it's like when you have it's like when you have 1 over 2x. When you differentiate this, you'll have a half. The half will keep there, but you differentiate what is differentiable. What is differentiable? So since ln u is differentiable, it is 1 over u, but 1 over ln 2 will keep there. Now it implies that by looking at this, we've gotten what our dx is equal to. Now we can substitute into this integral so that we have the integral of 2x, we called it u from here, then times dx, which dx we said is 1 over ln 2 times 1 over u, of course, du. Okay, we can put out 1 over ln 2. So I would say 1 over ln 2 will be the same as integral, u will go, so it will be du, which is when you integrate du, you get u. So it will be 1 over ln 2 u plus a constant of integration. But u is 2x, making it 2 power x out of ln 2, which is this one here. So this is how we simply come up with that integral. Very easy, very easy. It's just a matter of time and practice. Then we can continue. After getting the v dx, rather after getting v, now we can substitute in the by parts of ours. So it will merge out as an integral of x 2 power x dx is going to be equal to, we say uv. So u is x, v is 2x over linear 2 minus integral of v du dx. But v is 2x over linear 2. Du dx is 1, so I would just say dx. So this is the same as x. This pen is behaving in a funny way. 2x out of ln 2 minus, I can move out 1 over ln 2. Then I integrate 2 power x dx. So this is going to be equal to x 2 to the power x ln 2 minus 1 over ln 2. Then still by integrating this, you're going to still get 2 power x over ln 2, all right, plus a constant of integration. So this is going to come to, I can factorize out 2 power x over ln 2. I can factorize out 2 power x over ln 2, 2 power x over ln 2. Now here I will have x minus what? 1 over ln 2, because 2x over ln 2 is already outside. So I'm going to be left with x here minus 1 plus a constant of integration. As simple as that. Let me give you another dose. Let me give you another dose of a question.
Excuse me, teacher.
Yes, please.
Excuse me, teacher.
Yes, please.
Excuse me, teacher.
Yes, please.
I did not understand how you got. I did not understand how you got your dx here. I did not understand how you got your dx here on the side work.
Dx. I gave you an example that assume you are differentiating like 1 over 3, maybe x, 1 over 3x. What did you get? If you differentiate 1 over 3x, what do you get? Hello? If you differentiate 1 over 3x, what do you get? Oh. Okay, you get a third. The same, because this one is a constant, it is not differentiable, but x, you can easily differentiate x. And when you differentiate x, it becomes 1. The same applies here. If you have ln u out of a ln 2, ln 2 is like a constant, but ln u can easily be differentiated. When you differentiate ln u, it is 1 over u. When you differentiate, then this ln 2, it will keep there. So it will be 1 over ln 2, then times 1 over u. You get it? Thank
you, teacher.
Now from here, let's do some other example. And this example is the integral of 3 to the power root 2x minus 1 dx. Three to the power 2x root 2x plus rather minus 1. Now, when you look at this, you may not easily integrate just by rating, but you have to first work on this power, whereby we can maybe select, maybe like p to be equaling to that root of 2x minus 1. When you square either side, you're going to have p square is equals to 2x minus 1. The root will go. Differentiate both sides, you'll get 2p dp is going to be equaling to 2 dx. Now, implying that therefore our integral of 3 to the root of 2x minus 1 dx is going to be equaling to the integral of 3 to the power p, all right, of 3 to the power p. Of course, this 2 will cancel with this 2. So we have our dx as p dp. So instead of dx, we shall write p dp. This is what we are having. Now, by looking at this, we can now let our u to be equaling to p and our dv dp, not dx now. Our dv dp will be equaling to 3 to the power p. All right. So that our du dp will be equaling to 1 when we differentiate with respect to p, we get 1. And our v will be equal to the integral of 3 power p. And from what we have just looked at, this is going to be 3 power p out of ln 3. Interesting. So looking at this, we can merge it and we say that this implies that our integral of 3 p dp is equal to uv. Our u is p, our v is 3 power p over ln 3 minus the integral of v du dx. V is 3 power p over ln 3 du dp is now 1. So we just say dp. So it's going to be equal to p 3 power p over ln 3, all right, minus, I can move 1 over ln 3, then I say integral of 3 power p, then dp. Looking at this, this is going to be equal to, p 3 power p out of ln 3 minus 1 over ln 3 into the integral of 3 power p. This is the same as 3p again out of 3 power p again out of ln 3, then plus the constant of integration. But P is the root of 2x. So you substitute root 2x minus 1 times 3 to the power p, that is 2x minus 1 out of ln 3, then minus 1 over ln 3 times 3 power p, that is root 2x minus 1 over then 3, everything plus a constant of integration. We can factorize out 3 power 2x over ln 3. So it is going to be 3 power 2x minus 1 over ln 3 into what remain here will be the root of 2x minus 1, then of course minus 1 over ln 3 plus a constant of integration. So that is what we get as our result of integration. If well understood, type yes, and we go on. Good. So it's a matter of going through always. Otherwise, the things are very, very, very easy. Very, very easy. So from here, allow me take you to the ones that have evaluations, and let's say evaluate the first one from 0 to 1 of xe to the power negative x dx, and b 0 to 1 of xe3 power x dx. Now looking at this, I'll do one of them and you do the other. So which one can I do? Which one should I do? Because the approach is the same, and we have already looked at the direct integrals without limits. So when they put limits, may not change the meaning. So now we know, let me first integrate it without limits, then I put limits later. So we are going to look at x e power negative x dx. 0 maybe to 1, but let me say let u, even you can use basic technique, let u be equal to our x and dv dx e to the power negative x. So we say that our du dx here is 1, and our v, it is after integrating this, and we say that for this case, you drop the derivative as, since the derivative here is -1, we shall drop it as negative e power negative x. So from this we can have it that the integral from 0 to 1, x e to the power negative x going to be equaling to uv, which is negative x e power negative x minus integral v du dx. V is negative e to the power negative x, then dx. So this is going to be, of course, let me first leave the limits. So it's going to be negative x e to the power negative x plus, because of this, plus when you integrate e to the power x, you will have minus e to the power minus x. All right, so this is going to be equal to minus x e to the power minus x, then minus e to the power minus x. So when you put in the limits, it's going to be the integral of 0 to 1 x e to the power negative x dx is going to be equal to, now we put the limits in that expression we've got, minus x e power minus x minus e power minus x, all the way from 0 up to 1. So first substitute when you have a 1, so you will have minus, of course, this is minus. When you put a 1, it keeps minus, then e to the power minus 1. All right, then minus e to the power minus 1, that is 1. You cross that, then you bring in the 0 aspect, minus the whole of this thing is 0 because we are beginning with x and x is 0, so it's 0 minus e to the power 0. So this is going to be, if it is minus e minus another e, is going to be minus 2e to the power minus 1. Then this minus negative 1, because any number to the power 0 is 1, so plus 1. This is the same as, of course, the same as negative 2 over e, because you're having e to the power negative 1, meaning if it moves down to be negative 2 over e plus 1, which is the same as 1 minus 2 over e. And since your calculators have got e, you just substitute and see if you are getting the answer like that of mine, 2642. Substitute and see if you get the answers like those of mine. I don't know whether it's network, because members are logging out. I see people have failed to connect to their audios. I don't know if the problem is the network. It's not clear. Okay, so that is what we are having when we integrate that. That's what we are having when we integrate that. Then now from there, we can go to a different section of integration. And now we are going to look at integration that involves polynomials and inverse trigonometric functions. Polynomials and inverse trigonometric function. All right. And now, polynomials and inverse trigonometric functions. For this case, we shall be having inverse functions together with trigonometric inverse functions together with the polynomials. Okay, now right away to examples. Find an integral of sine inverse of x dx b integral of x tan inverse of x dx c integral of x integral of cos inverse of x over a dx. This one shouldn't worry you. The approaches do not differ. Then that is 1, 2. Show that the integral of 0 to 1 in x sine inverse of x is equals, of course, dx is equals to pi over 8 or 1/8 pi, 1/8 pi. So I'm going to do what I can, and I leave you with something here to do. So we are going to have integral of sine inverse of x. Now, one may be like, now, how is it by parts? I have one part of sine inverse. What is another part? What you need to do here, simply tell me that integral of sine inverse of x dx is the same as integral, another part you bring it in by yourself, and that is 1 times, because when you multiply 1, it will keep the same, but it will bring in another part. So 1 times sine inverse of x dx. Now, from LIATE, if you are to remember, you see logarithmic, inverse, algebraic. Now, who is going to tell me what my u is? What will be my u here? Let u equals to what? What is my u equal to?
Sine inverse.
U is the sine inverse of x. Because an inverse function comes before an algebraic function. So u is sine inverse of x. It means that now my dv dx is equals to 1. Okay, now du dx. This one takes us back to differentiation of inverse functions. Sine inverse of x, how do we differentiate it? So du dx. We said that when we differentiate sine inverse of x, we get 1 over root 1 minus x squared. Reminder. However, you don't need to remind us in an exam, just need this. But reminder is that when you are differentiating sine inverse of x, maybe we rate. let maybe y equals to sine inverse of x. It means that sine y is equals to x. When you differentiate both sides, you get cos y dy dx is equals to 1. But from this identity of sine squared x plus cos squared x is equals to 1, you can really see that cos squared x is 1 minus sine squared x. When you take the root, you get cos x as the root of 1 minus sine squared x. But that is in terms of y. So we shall say that 1 minus sine squared y under the root, then dy dx is equals to 1. So 1 minus sine squared y, if sine y is x, then sine squared y will be x squared under the root. Dy dx is 1, implying that dy dx would be equaling to 1 over root 1 minus x squared. So it shouldn't worry you that I called my sine inverse of x, its derivative, as 1 over root 1 minus x squared. Interesting. So this is going to come to, this one comes to, if you have dv dx, it means that our v is the integral of 1 dx, which is x. Now this is our x. Now it implies that the integral of sine inverse of x is going to be equaling dx, of course, is going to be equaling to uv, but our u is sine inverse of x, so it is going to be uv, and v is x, so it is going to be x sine inverse of x minus integral of v du dx. V du dx, so v is 1, v is x, then v du dx. My du dx is what? V du dx, so it is going to be times 1 over root 1 minus x squared dx, right? So this is going to be equal to x sine inverse of x minus the integral of x out of the root of 1 minus x squared dx. First, work on the integral of this. For integral of x out of root 1 minus x squared dx, we can let u to be equaling to 1 minus x squared. This one down, so that my du is equals to negative 2x dx. So that if I need dx only, it's going to be dx is equals to negative 1 over 2x du. In other words, I've divided by negative 2x both sides. So implying that the integral of this x over root 1 minus x squared dx is going to be equal to integral of x over root 1 minus x squared. This one we called it u, so it is going to be u power half because of the root, times dx. My dx is is negative du over 2x. X will cancel with x, so I will have this u can move up. I can move a half outside, so it is going to be negative a half integral of u power negative a half du. U power negative a half du. Now, when you integrate here, we are going to increase the power by 1 and we divide by the new power. So it's going to be equal to a half negative a half. When you increase the power by 1, it's going to be negative a half plus 1. It will be power a half. Then we divide by the new power, which is a half, which will be 2u to the power a half. Of course, plus a constant of integration. So this is going to be equal to, this will cancel with this 2. So you'll have your negative u to the power a half plus a constant of integration. But you know what your u is equal to, of course. So this is going to be negative u is 1 minus x squared to the power a half. Now you bring this integral of x, you bring it here. So by substitution, it is going to be x sine inverse of x minus the integral, but this integral brings negative also, so it is going to be plus 1 minus x squared power half, which is the root of 1 minus x squared, then plus a constant of integration. So this is how far it has brought us. That is how far it has brought us. Is it understood? Could there be any question? Could there be any question? Any query? So where there arises a need of reminding you with the previous applications of differentiation, I have to always go back so that you get the concept very well. Okay. Let me differentiate the second one, x tan inverse of x. Let me actually integrate x tan inverse of x dx. Well, for this particular case, we are going to let, okay, we are going to let our u to be equal to tan inverse of x and our v, or rather our dv dx, to be equal to x. All right. So when you integrate, when you differentiate du dx, when you differentiate tan inverse, it's going to be 1 over 1 plus x squared, which I'm going to prove to you this again. Then our v will be the integral of x dx, which is the same as a half x squared, or x squared over 2. Now, reminder of this, I want you to remember that when you're differentiating tan inverse of x, we can let it to be, let me use y again, as tan inverse of x, implying that tan y is equal to x. When you differentiate both sides, when you differentiate tan y, you get sec squared y dy dx is equals to 1. But sec squared y is the same as 1 plus tan squared y. The whole thing dy dx is equals to 1. But tan y is x, meaning tan squared y is x squared. So 1 plus x squared dy dx is equals to 1, making dy dx as 1 over 1 plus x squared. Very good. So now we plug in. So we're going to have our integral of x tan inverse of x dx as uv. My u is tan inverse of x, then v is x squared over 2. So I'm going to write it as a half x squared tan inverse of x, a half x squared tan inverse of x minus the integral of v du dx. V, which is a half, so I can move that a half. Then du dx, of course, we have v as after moving out a half, I'm left with x squared. I'm left with x squared over 1 plus x squared. Because it is this part after a minus, it is the same as v du dx. V du dx. Okay. Today's network is not very good because of it being a Monday. I guess many people are at work using this internet. We pray it settles. So it is a half x squared. That is, this part is uv. Then when you put minus, you put v du dx, then dx. So shall have dx like that. Now this is going to be equal to x squared tan inverse of x out of 2 minus a half, I'm repeating the step, sorry, x squared over 1 plus x squared dx. Now, you really need to know that this one here is an improper fraction. That's why you first looked at by parts. Rather, we looked at partial fractions and integrating of improper fractions. We say that an improper fraction is where you find the highest degree in the numerator is greater or equal to the highest degree in the denominator. So in other words, this is improper. So you need to first use longer division to come up with an expression. Okay. So by long division, if you work on this, by long division, you'll be having, okay, let me say for the integral of x squared out of 1 plus x squared dx. By long division, we are going to have, we are dividing x squared by x squared plus 1. So it's going to be, it's going to be equal to x squared divided by x squared, that is 1. 1 times x squared, that is x squared. 1 times 1, that is plus 1. Remember here, there is nothing. There is a 0, sort of. When you subtract here, this is a 0. Then 0 minus 1, that will be negative 1. So here we have negative 1 as a remainder. So implying that our function, our integral of x squared, in other words, okay, our x squared over 1 plus x squared is the same as 1, this 1, the quotient, of course, plus what remains. So it is minus 1 over 1 plus x squared, or x squared plus 1. Now, this is a reminder from the partial fraction. So now it means that our integral here of x squared over 1 plus x squared dx is the same as the integral, okay, the same as the integral of this, of 1 minus 1 over 1 plus x squared, all right, then dx. So the whole thing now, the whole thing is going to become, let me draw my pages like this. my whole thing is going to become, of course, from here, x squared tan inverse of x over 2 minus a half integral of 1 minus 1 over 1 plus x squared dx. Well, this is the same as x squared tan inverse of x over 2 minus, we split it, so it will be minus a half integral of 1, so it is the same as integral of dx, then minus minus, which is plus a half integral of 1 over 1 plus x squared dx. Well, this is the same as x squared tan inverse of x over 2 minus, when you differentiate dx, you get x, so minus a half x, right? Then plus a half, this is by tan substitution, which comes up with tan inverse of x plus a constant of integration. This one, I guess all of us can at least know where it comes from by looking at the tan substitution. Now, we realize that this one can reduce to what? This one can reduce to, I can factorize out a half, because a half is very common. And, if you move out a half, you'll be just left with here, you'll be left with x squared here we can say plus 1, so that will factorize out the tan inverse of x, then minus this x. And that is the final answer plus a constant of integration. It gives us the final answer. This is a half tan inverse of x, x squared tan inverse of x. So I moved out a half. It's the same as, but because this one also had a half, I had to generally move out a half. Then for this one here, x squared plus 1, it is as a result of this x squared. Then here is a 1 because I've already moved out tan inverse. So that is how best one can get the answer. So this is that is what I would expect one to get. Now, from here, I want everyone who is attending, to do that part C. I want to see if everyone can do part C and you get the answer as an integral of cos inverse of x over a dx as x cos inverse of x over a, then minus the square root of a squared minus x squared plus a constant of integration. I want to see if we can do that. Yeah. I want to see if we can really do that. So here, this one would not, still you need to know how to differentiate cos inverse. Just let cos inverse of this to be equaling to y, then cos y to be equaling to x over a, and then you continue like that. I'm just giving it to you as a trial question. So me, I'm going to work out this integral where I'm required to show that I'm going to show that the integral from 0 to 1 of x sine inverse of x dx is equals to pi over 8. So let's see how possible it is. I'm going to let my u again to be sine inverse of x and my dv dx to be equaling to x. In case they don't put anything here and you see an inverse, just a 1 must be put so that you move properly. Looking at this, we had already seen the derivative of sine inverse and we had already proved it. So du dx is going to be equal to 1 over root 1 minus x squared, and v will be x squared out of 2. So that my integral, let me first discard the limits, x sine inverse of x dx is going to be equaling to uv. So it is going to be x squared sine inverse x over 2. That is my uv. Then minus the integral of v du dx. Now I can move out because of v, and you see a half element, so I can move it out. You see minus a half. Then v du dx, so it will be x squared over the root of 1 minus x squared, then dx. Well, you can really see that here, this is taking up the element of sign substitution. Actually, this is the main reason as to why we look at sign substitution, tan substitution before we come to this far. So this is sign substitution. Automatically here we shall apply the sign substitution. So what are we going to do? We are going to first consider, let me say now, for the integral of x squared out of the square root of 1 minus x squared dx. We shall let x to be equaling to sine theta, because this is already x squared, and here we already have a 1, so there is no need of factorizing anything. So we let x equal to sine theta. If you missed any of these, I uploaded in all these videos of sign substitution, tan substitution, partial fractions on the YouTube channel. So you can go replay and you view how all these come about. So let x equal to sine theta, implying that my dx is going to be equal to cos theta d theta. When you differentiate sine, you get a positive cos. However, when you integrate it, you get negative cos. So now we are going to say, that this implies that my integral of x squared out of root 1 minus x squared dx is going to be equal to x squared over, we say that x is sine theta, meaning that x squared is sine squared theta. So it is going to be integral of 1 minus sine squared theta, then d theta. My d theta, rather, my dx, sorry, is going to be cos theta d theta. This is the same as the integral of x squared over 1 minus sine squared theta is cos squared theta. Under the root is cos theta. So this is cos theta times cos theta d theta. This one is cancel. And after them cancelling, After them cancelling, we shall have the integral. Remember, x is a sine theta. Oh, yeah. X is sine theta, meaning that x squared is a sine squared theta. So sine squared theta d theta, because cos will die. Now, this one now takes us to even powers, integration of even powers. Oh, very interesting. Let me put my equal signs here. So integration of even powers. You need to know how sine squared theta is expressed. We express sine squared theta in half angles or double angles as a half. So it's going to be an integral over half. Then 1 minus cos twice theta.
1 minus cos.
Now, d theta, which is equal to a half theta. When you integrate one, you get theta. So it is going to be a half theta. When you integrate cos 2 theta, you get a half cos 2 theta. But because of this half, it will be minus a quarter sine 2 theta plus a constant of integration. Wow. I feel like splitting this further because trigonometry comes on board. So this is, allow me to say, a half theta minus a quarter. Sine 2 theta can be called 2 sine theta cos theta from our trigonometry plus a constant of integration. 2 we reduce a 4 so that we get 1 over 2 theta. The theta is not down, but 1 over 2 theta, then minus a half of sine theta cos theta plus a constant of integration. But we know if x is sine theta, then theta is the sine inverse of x. So now this is going to be a half sine inverse of x minus, now this is sine theta cos theta. Sine theta cos theta, all right? This is sine theta cos theta. What does it imply? Sine theta cos theta. If we have sine theta cos theta, of course, we know what cos theta is equal to in terms of sine theta. Cos theta is the same as 1 minus sine squared theta. So we shall have a half. Let me first show you. You will have a half, all right, into sine theta. Yes, sine theta, that is x. Then you cos theta. Cos theta is the same as 1 minus sine squared theta under root. So it is going to be root of 1 minus sine squared theta, which will be x squared. All right, then plus a constant of integration, because everything must come back to x. So here you can really see that sine theta is x. Anyway, this is the same as a half sine inverse of x minus a half x root 1 minus x squared plus a constant of integration. Is that okay? Is that okay?
Yes, teacher.
Yes, teacher.
Very good. Now we bring in the limits. Now we bring in, before the limits, this was just for this part, which is this. Now we still have this a half. We have to substitute everything. So this would imply that our integral of x sine inverse of x dx is going to be x squared sine inverse x over 2 minus a half into the integral of that, which is a half sine inverse of x minus a half x root 1 minus x squared plus a constant of integration. All right, this is going to be equaling to x squared sine inverse x over 2, it goes to minus a quarter. I'm multiplying a half inside, minus a quarter sine inverse of x, then plus a quarter x root 1 minus x squared plus a constant. Then we bring in the limits. Now, let me bring in the limits in another page. So I'm quoting this. I am quoting this. Let me first capture it and I go with it. So now, when you put in the limits, it's going to be integral from 0 to 1 of x sine inverse x dx is going to be equal to, now we put, it is going to be a half x squared sine inverse x minus a quarter sine inverse x plus a quarter x root 1 minus x squared from 0 up to 1. It's going to be equal to, first put a 1. First put a 1, it's going to be a half times 1 times sine inverse of 1 minus a quarter sine inverse of 1. All right. Then, of course, since this is 1 here minus 1, the whole of this is 0 under root 0, so the whole of this is 0. So we shall have that minus, we put a 0. If you put a 0 here, it's going to be 0. Sine inverse of 0, 0, 0. So you subtract a 0, you're going to have a half sine inverse of 1. Sine inverse of 1. The whole of this one will come up with 45. It's better you put your calculator in radians, or you can put it in degrees and then you convert to radians later. But this one here gives us pi over 4. Then a quarter sine inverse to give us pi over 8. All right, is it 8, 2 minus pi, which is going to give us pi over 8. As simple as that. So that's what we can manage getting. And now our next lesson, of course, I want to go beyond this, but our next lesson, we are going to be looking at polynomial and logarithmic functions. As far as I'm concerned, and as far as I'm aware, we are left with 3 cases. We are left with 3 cases. Then we look at T substitution, splitting numerator, and we complete integration. 2 lessons are enough for us to come to the end of integration. And then we either start complex numbers or differential equations. I wish you the best of the day. Then, before I move, members, we have got into the new month. You know what it means. Let's do everything as early as possible. But on the timetable, there is inorganic chemistry, there is inorganic chemistry at 11. So I want us to agree and have this lesson at 2 p.m. I want us to agree and have this lesson at 2 p.m. Is it okay? Is it okay to us?
Yes, teacher.
Okay, let's have our inorganic lesson. I had recorded it. What did you get after integrating ln x? That is where we are going. That is where we are going. Don't worry, because when we say logarithmic functions, now we are going for lns. So those of ln x, whatnot, all of them are going to come in the next lesson. Everything will be captured on Wednesday as far as integration is concerned. So I'm saying that our inorganic chemistry lesson is at 2 p.m. I woke up early, recorded a lesson, but forgot to save it. So I spent all 1 hour and forgot to save the recording. So I wasted my time. But anyway, these are three things. These are three things we are going to meet after lunch, and we cover the inorganic part. Members, thank you for attending. At the start, the number is not bigger, but God willing, we shall increase. I wish you all the best. Stay blessed.